Good morning, afternoon, or evening. How y'all doing today? Welcome back to Mr. Morrow's Honors Geometry class. Today we're going to be talking about radicals and quadratic equations. Very important skills that you learned in algebra, but you're going to see them a lot in this chapter. We're going to be working with things like the Pythagorean theorem. We're going to be working with special right triangles, and radicals are going to dominate this, okay? So right quick, when you're looking at a radical, see this radical here, you see this n and a radical sign and x to the m. The radical sign itself is called a radical. This little n here, that's in red here, that is called an index. The inside part of the radical, circled in blue, is called a radicand. And this exponent of the radicand is literally called the exponent of the radicand. When you have a radical, you can convert that into a base with what's called a rational exponent or a fractional exponent, bless you, as such. When you have the nth root of x to the m power, the n becomes the denominator of the rational exponent, and the m becomes the numerator of the rational exponent. So in real application, the third root of x squared would be x to the 2/3. Does that make sense? How about I saw you shaking your head. You got it? Okay. So what would just the square root of x look like? Please remember that when you have a square root, there's an invisible 2 here. It's invisible. You'll never see a 2 there. But if it's invisible, please know if there is a 2, there's also an invisible 1 here. For the variable. Every variable has an invisible 1 to the top of it as an exponent, unless it's otherwise denoted. So there's an invisible 2 and an invisible 1, so this will become x to the 1/2. If I have a cube root of x is x to the 1/3. Okay? Very important skills here, so please don't forget. Okay, next. To simplify a radical, the best thing to do is to memorize your perfect squares. If you memorize your perfect squares, you can look at 14 right off the bat and say, hey, wait a second. This is 16 times 3. Square root of 16 is 4 with a leftover 3 inside of my square root. Now, if you don't know your perfect squares very well, which I strongly suggest that you do, you're going to have a big problem. You're going to have to go down a longer path. And this longer path would include breaking down this number into what's called its primes. So if I didn't know that it was 16 times 3, this is 2 times 24, 2 is a prime. 2 times 12, 2 is a prime. 2 times 6, 2 is a prime. 2 times 3, 2 is a prime. The beauty of this radical, the index rather, it tells the reader, hey, dude or dudette, you need this many of the same number to pull out one of those values. So since there's an invisible 2 here, I need a set of 2 of the same number to pull one out. So a 2 and a 2 comes out as a 2. A 2 and a 2 comes out as a 2. There's no other sets of 2s, so I'm left with a radical 3. 2 times 2 is 4, radical 3. Okay, let's just say for giggles that this was the cube root of 48. Let's break it down the same way. 2 times 24, 2 times 12, 2 times 6, 2 times 3. In this case, my friends, I'm looking for sets of 3. So I need 3 of the same value to pull one of those values out. So I've got a 2 and a 2 and a 2, which comes out as a 2. And I have a leftover of cube root of 6, because that is what's left over in the radical. You promise me you guys got this? You sure? Okay. Next. When I want to add radicals together, I need the same radicand. I cannot add different radicands together. So I cannot just add 18 plus 32 plus 75. That is an illegal mathematical operation. But what I can do is simplify each of these to try to have the same radicand. So I'm going to do this the way I know you guys are going to get to do this quickly because you're going to remember your perfect squares. 18 is 9 times 2. So square root of 9 is 3, radical 2. Plus 32 is 16 times 2. Square root of 16 is 4, with a radical 2 left over. 75 is 25 times 3. So I got square root of 25 is 5, with a radical 3 left over. I can add these two because they have the same index and the same radicand. So this is 7 radical 2 plus 5 radical 3. Okay? Does that make sense? Okay. When I have a fraction and a radical, I can split up this fraction into a numerator and a separate denominator. Very important. So this will become the square root of 5 over the square root of 3. But I am not legally allowed to have a radical of 3 in the denominator. Well, let me rephrase that. I cannot have any radical in the denominator. So what I must do is called rationalize. When I rationalize, I want to multiply the numerator and the denominator by the square root that will make the denominator a whole number. So in this case, I've got a square root, right? How many 3's do I need to pull one out? I need 3, guys? Guys, I've got a square root of 3. Isn't there invisible 2 here? How many 3's do I need in total to pull 1 3 out? 2. How many do I have right here in front of me? So what do I have to multiply by? By a square root of 3. This will give me the square root of 15 over the square root of 9, which is the square root of 15 over 3. You can go ahead and eliminate this step. Why? There's a very powerful theorem that states the square root of x times the square root of x equals x. Why? Because the square root of x and the square root of x is the square root of x squared. And a power of 2 cancels out a radical of 2, a square root. So when you multiply the square root of a certain radicand times the square root of that exact same radicand, the answer is simply the radicand. Does that make sense, guys? You promise? Okay, now look. Here's where it gets a little bit tough. Let's just say I had a cube root of 2 over a cube root of 5. In this particular case, in this cube root of 5, how many 5's do I need to pull 1 5 out? You need 3. How many 5's do I have right now? So how many do I have to multiply to both top and bottom? 2, guys. So I'm going to multiply by the cube root of 5 squared. So this will become cube root of 2 times 25, so that's the cube root of 50, over 1 5 times 5 squared, isn't that 5 cubed? Do I need 3 5's to pull out 1 5 from a cube root? So that becomes a 5. Does this make sense, guys? Now would be the time to ask. Yes, sir. You can simplify 50. 50 is 25 times 2. 25 is 5 times 5. Do I have 3 5's there to pull out a 5? Do I have 3 2's there to pull out a 2? So I can't do it. If I was able to, I would, but I can't. Thank you, sir. Any other questions on this so far? Okay. Now, factoring and solving. Okay, guys, this is huge. This goes back to algebra as well. When you are given something as such, x squared plus 9 equals 25, I'm going to have to sometimes ask you to solve for x here. Okay? You've got 2 different methods here that you can use. When it's nice and simple like this, and you just have an x squared and numbers, you can use the square root method. And the square root method works as follows. X squared plus 9 equals 25. Let's subtract 9 to both sides. X squared equals 16. Remember what I just told you in the slide before. I can cancel out a power of 2 by taking the square root of both sides. So this square root cancels out that power of 2. So x will equal now plus or minus 4. Why plus or minus, Mr. Morrow? Well, what's 4 times 4? What's negative 4 times negative 4? 16. So there's 2 roots. Now, for our purposes in geometry, you are usually going to use the positive root only. Why? Because you cannot have a negative side or a negative distance. So this is the square root method. Factoring method. If I wanted to factor this bad boy, x squared plus 9 equals 25. I'm going to bring everything over together to one side. So I'm going to subtract 25 to both sides. X squared minus 16 equals 0. I don't know if you guys remember this, but this is called a difference of squares. Since x squared is a perfect square and 16 is a perfect square, you factor out a difference of squares by finding the square root of the first plus the square root of the second times the square root of the first term minus the square root of the second. And now you activate what's called the zero product property. The zero product property states that if A times B equals 0, then A can be set equal to 0 and B can be set equal to 0. So in this particular case, my x plus 4 is A, my x minus 4 is B. So I can set x plus 4 equal to 0 and x minus 4 equal to 0, and x will still equal plus or minus 4. I don't care which way you use. I'm just here to teach you the possibilities. Okay? Now this is the easy part. These are easy factorings. What do I do in a case like this? Well, in this particular, okay, yeah, you got something for him, my man? Okay, very, very smart. I'm very proud of you, son. Very proud of you. 3 times the square root of 5 squared, that means that it's 3 times the square root of 5 times 3 times the square root of 5. Plus 3 times square root of 2 squared means it's 3 times square root of 2 times 3 times square root of 2 equals x squared. My brothers, what's 3 times 3? 9. What's the square root of 5 times the square root of 5? 5. Very good. Why? Because square root of 5 to square root of 5 is 25. Square root of 25 is 5. Plus, what's 3 times 3? Times. What's square root of 2 to square root of 2? 2 equals x squared. So this is 45 plus 18 equals x squared. What does 45 plus 18 equal? 63. Very good. That equals x squared. How do I get rid of that power of 2 that belongs to the x? Very good. Square root both sides. What perfect square can I pull out of 63? It's 9 times 3. Very good. 9 times 7. What's square root of 9? 3. Square root of 7 plus or minus equals x. Yes, sir. No, you could not have squared the entire problem at the beginning. No. You want to first individually find the values, sir. And with all due respect, why would you square it? I think you meant, can you square root it? Yeah, no, okay. But you got to be careful with your wording, guys. When you tell a teacher, can you square, they're thinking, are you raising it to the second power? Can you square root it? That's different. Now, you could have, I guess, square rooted everything, but you're still going to have to simplify that and that. No, you can, if you square root this, it does not cancel these two out because there's a sum here. So you have to find a one complete value. Thank you very much, sir. Great question, actually. Any other questions so far? Talk to me, boys. Okay, let's continue. Let's solve each. Okay, now in this case, it's not going to be the square root method. Here, you're out of luck and you're going to have to factor. How do you know when to do what? When I have an x squared and an x, you have to either factor, complete the square, which is a bit of a pain, or use the quadratic formula. So I'm gonna hook you guys up right now. First, when you're factoring a trinomial, you got to create a trinomial. So you subtract 16 to both sides. So x squared minus 10x minus 16 equals 0. Your setup here, put an x and an x because you're square rooting that x squared. Now here's the question. What times what equals the c value, which is your negative 16, but when added together equals your b value, which is your negative 10? Negative 8 and no, can't be that. Can't be that. Cannot be that. Yeah, in this case, you cannot factor this. So you're going to have to use either completing the square or what is called the quadratic formula. The quadratic formula follows this. Negative b plus or minus the square root of b squared minus 4ac over 2a. The a is the value in front of your x squared. Your b is the value in front of your x. And your c is the value that has no variable at all. So in this case, it would become 10 plus or minus. Negative 10 squared is 100 minus 4 times a, which is 1, times c, which is 16, negative 16, over 2 times a, which is 1. Now, of course, you can use a calculator or you can simplify the radical. Really depends on the teacher and the type of test you're taking. On the SAT, they're going to want a simplified radical. So this is going to become 10 plus or minus the square root of 164 over 2. Now that 164 can be simplified. Square root of 164 comes from 82 and 2. And then this can be 41 and 2. So this becomes 10 plus or minus 2 square root of 41 over 2. This 2 can be divided to the 10 and the 2, giving me a 5 plus or minus square root of 41. This is big boy status now, guys. And all of this you learned last year. If you don't remember it, I suggest watching some of my videos on algebra to relearn it. Okay? Now, sometimes you can factor it, by the way. If this had been a positive 16, you could have factored it. What times what is positive 16, but when added together is negative 10? Negative 8, negative 2. Set both of them equal to 0, and x would have equaled 8 and 2. So if you can factor it, you factor it. If not, you use a quadratic formula. X squared plus 5x equals 0. What can I factor out of x squared and 5x? An x. So then I'll have x times x plus 5 equals 0. Set x equal to 0, set x plus 5 equal to 0, x would equal 0 and negative 5. You guys with me here? You guys with me, guys? Okay. Then I guess I jumped the gun in the first one. I'm sorry. When in doubt, use the quadratic formula to solve quadratic equations. Even if it's factorable, guys, but you just freak out and you don't know how to factor it, you can always use the quadratic formula. First, bring all the components of the equation to one side, creating a trinomial in the following form. Ax squared, a is always attached to the x squared, plus bx, b is always attached to the x, plus c. C is always the constant. Once set up, simply plug in the a, the b, and the c into the quadratic formula and solve. Although the quadratic formula is intended for unfactorable quadratic equations, you can solve any quadratic equation, any, using the quadratic formula. Always, any quadratic equation can be solved by this. So for example, in this case, would we need to use a quadratic formula here? No. In this case, I can go x times x. What times what is 10, but when added together is negative 7. Negative 5 and negative 2. Set them both equal to 0. X will equal 5. X will equal 2. However, if I wanted to put this into the quadratic formula, it would have worked. If I plugged it into the quadratic formula, it would have been negative b, which is 7, plus or minus the square root of b squared, which is 49, minus 4 times a times c over 2a. This would have been 7 plus or minus 49 minus 40 is the square root of 9 over 2. 7 plus or minus 3, because the square root of 9 is 3, over 2. Then I have two sets here. I have 7 plus 3 divided by 2, which is 5. And I have 7 minus 3, which is 4 divided by 2, which is 2. So you can solve it either by factoring if you see it, or by a quadratic formula if you don't. Always. Does that make sense, boys? You promise? Perfect timing then. Thank you very much. Hope you learned a lot. Have a wonderful day, and thanks again.